We are Team Nebraska, or better known as How About That, Nebraska. My name is Ed McNamara.
I'm Tess McCabe.
And I'm Ben Schnatz.
And due to unmitigatable circumstances, our architectural contingent was not able to join us tonight, and that would be Will, Morgan, and Jess. We would like to thank our professors behind us on this, Dr. H.A. Erdomish and Dr. Sharon Kuska, as well as our mentor, Sam. So for Howe Bridge design, it was developed in the early 1800s by William Howe. It was a modification of Long's truss that utilized metal components. Long's truss did not utilize metal components. It was a timber truss. In addition to adding metal components, he added compression wedges and steel tension rods. He was the first patent design to include a structural analysis of its members. And the first bridge that was of the Howe Bridge design was constructed in Warren, Massachusetts in 1839. A year later, in 1840, the Connecticut River Bridge was constructed. It was a massive bridge that spanned with 7 spans, each of 180 feet. And at the center deflection at each of the span only hit 1/4 of an inch upon railroad loading, which was pretty significant for the time. The bridge that we specifically referenced for this project was the Polk County Covered Bridge, also known as Owens Covered Bridge from the farm that it came from. It is located currently in Easter Lake Park near Des Moines, Iowa, which is a bit of a distance for us, but not enough of a distance that we can do it in a day trip and go check out our bridge. The bridge itself was constructed in 1887, but was relocated in 1939. Somewhere along the way, the covered aspect of the bridge and the moorings and foundation were replaced. But the truss system is the original and is typical of late era Howe truss bridge design that used timber wood beams, tension rods, and steel compression wedges. As we were looking into the Polk County Bridge, we discovered that there was another bridge within an easy drive distance of the Polk County Bridge that was of a similar design, being also the Howe style. And so we also went to check that out kind of as a reference. This bridge was the Hammond Covered Bridge. It was constructed in 1894. In addition to the iron tension rods and wooden beams, it utilized iron I-beams for its deck support, and we couldn't find out enough details to confirm how much of it had been replaced with time or how much of it was still standing. But the contrast between the Hammond and the Polk County Bridge gave us a chance to notice some distinguishing areas for potential problems, and those were basically the wood, the metal, and the surroundings. The covered bridge aspect of the typical the typical Midwestern bridge being that of a covered bridge. The covered bridge aspect was in response to multiple freeze-thaw cycles throughout the year that would require that the truss be protected from the elements more consistently. And so the main problem being that the truss should not come into contact with a lot of water, and therefore the bridge covering prevents that and also allows itself to be the sacrificial aspect of the bridge. So the wood, obviously, too much infiltration from water can cause rot, especially if neglected and not taken care of, especially at the joints. For the metal, it's a similar problem. Possible source of rust should water and debris be able to accumulate. And lastly, the surroundings, as water flows underneath the bridge, settlement can cause the structural foundations to weaken. And those were the main points we looked at for the durability of the bridge.
After we went and saw our bridges, we came back and set about doing analysis on a 3D model and based on the drawings that we got for our Owens Covered Bridge. We used 3 different methods of analysis. The first being the rules of thumb found in the 1893 Civil Engineers Pocketbook. We also conducted a static analysis using historic empirical methods, including method of joints and method of sections, which can be referenced in a practical treatise on bridge construction. And we also created a 3D model using SAP 2000. SAP 2000 stands for Structural Analysis. What's the third one, Ben? Program. That's, yep. Structural Analysis Program 2000. And so we used SAP 2000 to create a 3D model of our bridge and got internal forces of our members from there. Next slide, Ed. The first thing that we did after that was to derive our loads. We referenced ASCE 716 for both the load types and possible load combinations that our bridge would be undergoing. And we based the loads off of their respective sources. So for our contemporary analysis, we based the loads that went into the load combinations off of ASCE 716. Because we were analyzing the bridge as if it were built today following today's building codes. For the historic empirical analysis, we based our loads off of what we could find in a practical treatise on bridge construction, because the loads from there were from the loads of when the bridge was built. Over on the right, you can see the different load combinations that were given to us by ASCE 716. So we went through and used all of these load combinations, but we varied the type of load, the amount for each load based off of whether we were doing the contemporary analysis or the empirical analysis. Next slide, Ed. So as you can see here, we have the controlling load combination for the contemporary and the historic empirical loadings. At the top, you can see how the dead live, roof live, snow, wind, and rain loads factor in to the controlling load combination. And you can see the difference in those loads between the contemporary loading and the historic empirical loading. And interestingly enough, we did end up with the same controlling load combination for the historic empirical and for the contemporary loading, even though our maximum loading for the historic empirical was just a little bit higher than our maximum for the contemporary. And you can see how our dead loads are different than each other. Our lives are the same. The historic empirical did not take into account any roof live load, and the rain load for the historic empirical was higher than the contemporary load as well. So we then moved on and used the Civil Engineers Pocketbook of 1883, which has a very prescriptive design for bridge design. And so it first asks, are you designing a double road or a single road? Similar questions like that to narrow down which direction to send you in design. And so one of the things that we noticed is that it specified larger tension rods than what we would prescribe today. And it limited the maximum stress to less than 800 PSI for members. Over on the right, you can see a comparison of the rules of thumb and the actual dimensions of the bridge that the Civil Engineers Pocketbook would have prescribed for us. And then here for our empirical analysis, you can see some of our hand calculations for the method of joints and the method of sections. We used both methods for solving for the internal forces inside each member of our bridge. And if you would like to look through that, there are 8 pages of delicious hand calculations available for you in our report.
So as Tess said, for the contemporary analysis, we used SAP 2000, in which we were able to construct a 3D model of our bridge. So that model was based upon the dimensions that we took from our site visit to the Polk County Covered Bridge, as well as these plans that were put out by the Historic American Building Survey, which actually measured the bridge as well and developed the set of plans, which we accessed through a government database. So in SAP, as I said, we were able to develop a 3D model, and we were able to place our loading upon that bridge. So we placed a load of 223 pounds per square foot, and so we broke that down into a per foot per cord basis. So we applied 2,100 pounds per lineal foot per cord at the bottom. And under that loading, we were able to determine a deflection of 0.84 inches downward. Then SAP was also able to give us figures in which we were able to determine the internal member forces. So in the compression and tension diagram shown at the bottom, the red represents compression and the blue represents tension. At the top cords, the max tension was found, at the cross bracing, the maximum compression was found to be 670 pounds per square inch, and the tension rods, it was found to be 6,800 pounds per square inch. SAP was also able to give us shear force diagrams as well as moment force diagrams, the red being the positive shear and moment and the blue being the negative. The maximum shear found at the ends was 15,000 pounds under our loading, and the max moment at the ends was found to be 47,000 foot-pounds upon our loading. So from our SAP model, we use that to determine our ultimate load carrying capacity. We look to the member properties to determine our breaking points. So using the Forest Products Laboratory Wood Handbook, it told us that our bridge being made of white pine had a 440 PSI stress perpendicular to the grain and a 4,800 PSI stress parallel to the grain. The wrought iron had a max stress of 34,000 PSI. So then comparing that with our design loading, looking at our tension rods, the pink purples at the bottom of the chart there, we were well under that. So our problem members would be in the loadings, in the members which would receive perpendicular loading, which would be our blue members. So under the design loads, our blue members were under 570 pounds per square inch of stress. So we deemed it necessary to take that number down to the 440 pounds per square inch limiting. So using SAP, we were able to go through multiple iterations in order to achieve that stress in those blue members, in which we were able to determine our maximum loading to be 1,600 pounds per cord. Under that loading, the deflection was found to be 0.66 inches downward.
After we went through and did all of our analysis in SAP and using the engineer's pocketbook and empirical analysis, we then had to transition from analysis to design for phase 3. And so we had to take our model of the Polk County Bridge and translate it into something that was constructible for us while still retaining structural integrity. So we used our SAP model to determine which members needed to be stronger than others because they were carrying more load. And then from there, we idealized our bridge model by removing tension rods and compression blocks and simplifying our cords and cross bracing on all sides to create a bridge model that we could construct ourselves. And then on this slide, you can see our idealized design of the Polk County Covered Bridge. We used red oak and poplar for our wood choices. Red oak because it had the strength that we needed per square inch, and poplar because we could find it in the dimensions that we needed, and it was light enough that it would work for our decking. For our connections, we used oak pegs for all of our connections for our decking, and then we used deck screws for all other connections. Next slide, Ed.
For our material weight at the end of the construction, we ended up with 43 pounds of timber and a measured 1 pound of metal, coming to our metal composition as a weight of the overall bridge of 2.27%. That number can be a bit misleading because we included excess screws for our actual build so that we would not have to scrounge or fight for that last one. and we had quite a few screws left over.
So per the specifications, we had to do a vertical load test as well as a lateral load test on our bridge. So in order to do the vertical load test, we measured out 500 pounds of bricks in which we were able to load in 2 piles upon the deck of our bridge. We measured the deflection at 3 points, the left and right end deflections being less than a 1/16 of an inch upon loading and the center deflection only being 1/8 of an inch. At the same time, we also looked at our lateral sway as we were loading it, which came to be 0. Under the lateral loading, 2 of our members held each end of the bridge while 100 pounds was placed on the deck. At the same time, a 3rd member pulled horizontally on our bridge with a scale which measured a force of 38 pounds. We were required to pull 35 pounds on it, but it was measured with a luggage scale, so to account for inaccuracies, we went a little over. And under that loading, the sway was still found to be 0 inches.
Well, we thank you for your time. That's been our presentation.
Hello, we are the Columbia GSAP Historic Preservation Team, and we will be presenting on the Beaver Kill Covered Bridge. This team consisted of second-year Masters of Science students in Historic Preservation, Bruno Elias, Katie Foster, Emily Kahn, Will McCallum, Tom Rice, Tucker Simmons, and Madison Story, and PhD student in Historic Preservation, Anna Gasha. The team comes from an interdisciplinary background, containing 1 engineer, multiple architects, a historian, and individuals from other allied disciplines. In this presentation, we will provide an overview of the bridge's history and design, structural analysis, and durability, and discuss our building and testing process. We modeled our bridge off of Beaver Kill Covered Bridge, hereafter BCB, in Sullivan County, New York. Built in 1865, this bridge is an example of the town lattice truss, which was patented by architect Ethiel Town in 1820. Consisting of closely spaced wood plank members laid diagonally across each other and attached with wooden pins at every intersection, the town truss was a significant development in early covered bridge design, as it allowed bridges that could span long distances with less skilled labor and weight than the burr truss. BCB was listed on the National Register of Historic Places in 2007 due to its significance in bridge engineering and role in developing the surrounding town. It underwent an award-winning restoration in 2017. The primary reason we chose this bridge was for its historical significance as a representative example of surviving historic covered bridges in New York State. According to data compiled from the New York State Covered Bridge Society, there are 19 surviving pre-1890 covered bridges in New York. Of these, 52.9% are supported by town trusses, shown in maroon. The BCB thus represents the history, construction, and preservation concerns of New York's dominant covered bridge typology.
The town truss was designed to span long distances with minimal weight and less need for skilled labor in construction. The Hill covered bridge is a variation on the patented town truss with 4 radiating planks at the end of the truss to distribute shear forces at the supports over a series of members, eliminating the need for bolster beams or abutment seats. For the structural analysis of BCB, we used Rhino and Grasshopper with the Carumba 3D finite element analysis plugin. The structural analysis considered dead and live loads, as well as snow and wind loads based on the BCB's geographic location. Contemporary bridge standards, such as the Wooden Bridge Manual for the U.S. Department of Agriculture, were used to gauge the serviceability of the Beaver Kill covered bridge. Under gravity loads only, the Carumba analysis verified that the truss exhibits typical truss behavior comparable to a simply supported beam. The flexural moment is resolved through a force couple in the chords with the top chord in compression and bottom chord in tension, as shown in the figure above of the axial loads in the members. The bottom chord tension force is approximately half the top chord compressive force, likely because the beam supporting the floor beams acts as a second bottom chord. For gravity loads, the bridge performed well in terms of serviceability, with displacements of L over 470 for live loads and L over 380 for live and dead loads. These show decent factors of safety over the recommended maximums of L over 360 and L over 240, respectively. Under lateral wind loads, the bridge model showed significant deflection. However, at the actual BCB, this deflection would be counteracted by the buttresses, spaced evenly along the outer walls, the steel rods tying the truss together at the top chord, and the knee bracing of the roof structure. As a final note, the trunnel connections used at the vast majority of joints in the bridge were not examined in detail with this modeling. However, based on the axial loads that would be transferred in shear through the connections from our analysis, it's anticipated that trunnel failure is a critical mechanism for potential failure and should be part of inspection and maintenance plans for the structure. Based on a conditions assessment conducted via Google Maps per COVID-19 restrictions, the Beaver Kill covered bridge appears to be in good condition with no reverse camber. However, the siding does appear weathered, and some potential isolated deterioration may need to be addressed. Wood decay is a typical decay mechanism for covered bridges, and town lattice trusses commonly experience decay at connections, among other issues. Finally, hemlock, which the Beaver Kill covered bridge is constructed of, has low decay resistance. With those things considered, potential isolated deterioration that may require structural intervention in the form of member splicing or replacement may need to be addressed pending a more thorough inspection. Because of these issues, yearly inspection and maintenance are central to the bridge's long-term preservation. This should include the removal of vegetation and debris, inspection of roof and siding boards, inspection of concrete abutments, and snow removal. The bridge was historically unpainted, so a coating should only be considered following repeated board replacement.
The main takeaway for us from the building process is a deeper appreciation for the craftsmanship and construction planning and skills required. Even though the town truss was meant to reduce the amount of skilled labor required, we found that managing the connections that had overlaps of both cord members and 2 diagonal webs going in different directions was very tricky and hard to plan for with our limited background in carpentry and the institutional guidelines for gathering in New York City and specifically Columbia University. Our build took us a lot longer than anticipated, largely because we had to find workarounds due to connections not working out as anticipated. The trunnel connections were especially difficult due to the fact that scaling them down made them fairly slender elements that tended to buckle or snap as we tried to hammer them in. As we briefly mentioned in the structural analysis section, we had reservations about this in our analysis. We acknowledged that the contemporary modeling software does not accurately model traditional carpentry joints often employed for timber bridges like PCB. We ended up modeling the truss with fixed joints consistent with other computer model analysis of timber truss bridges in the literature. And since all connections in the actual bridge have at least 2 wooden dowels, which should minimize the amount of rotation. Beyond these theoretical considerations, the building process also made clear that trunnels were both difficult to place consistently, which in turn made their structural capacity unreliable at times. Also, we were often relying on 1 trunnel per connection due to the limits of member sizes. The connection acted more like a pin connection rather than a fixed connection. We would be curious to see how the actual connections at the BCB are faring in light of these discrepancies. As anticipated, the result was the trunnel failure when vertically loaded on the decking. These photos demonstrate the shear failures at these connections. Following the loading procedure from the competition specifications, our bridge underwent a sudden failure due to the trunnel connection, and the decking detached from the bottom of the bridge as we loaded. However, we decided to continue loading from the top of the bridge instead of the decking in a modification of the specifications, since we determined that there was, in fact, still a valid truss bridge load path remaining due to the fact that the bridge had 2 bottom chords and only one had failed. We verified that the detached decking and lower bottom chord were not touching the floor in order to ensure that the load path was not counting on an additional support. So we continued loading the model at the roof level with weights. This demonstrated the relative robustness of the bridge construction despite the initial failure of the decking. Thank you very much, and we look forward to your questions.
Hello everyone, welcome to Texas A&M University, Kingsville. Today we're going to be presenting you our research and redesign of the Mox Covered Bridge in Vermont. When we started this competition, we designated certain topics to each of the team members. I wrote the historic code section of our research, Kelly Dodd and Jacqueline Garcia examined construction materials and historic research, Maria Garcia performed a structural analysis on our design, and John Ruiz studied durability and preservation methods. To help us, we had 3 professors from our university, Dr. Ginniga, Dr. Bailey, and Mr. Glusing. We also had Patrick Sparks from Sparks Engineering as our mentor. With the help of our mentors, we were able to see our project from different views, and their praise and criticism guided us as we made progress.
Located in Orange County, Vermont, the Moxie-covered bridge stretches across the First Branch White River in Chelsea, Vermont. The structure material is comprised of timber with iron rods added for support. It was registered to the National Register of Historic Places on the date of September 10, 1974, by the time the Preservation Act of 1966 came into effect. The Moxie-covered bridge was one of the only covered wood bridges within a 7-mile radius to have survived in the town of Chelsea. For the historic research and design, we identified the Queen Post Truss design as an expansion of the King Post. Additional members may be used as counterbrace as seen within the modified queen post truss. As a continuation for the building materials, the Moxie-covered bridge consisted of 2 timber queen post trusses and incorporated iron suspension rods extending from the diagonal braces upper vertices to the base chords. Heavy timbers are set together to form trusses. The wood floor consisted of planks laid in parallel to the trusses, sidewalls are sheeted with flush boards hung vertically, and the portal openings are bordered with semi-elliptical arches. The gable roof is covered with corrugated metal sheeting.
I'm going to talk about the structural analysis for our bridge. The relevant loads considered for calculations were a combination of live and dead loads. Dead loads considered of self-weight and live loads considered were older transportation methods such as a horse and buggy, along with newer methods of transportation such as a compact car. The purpose of comparing those two were to have a better understanding of the purpose of the first design and furthermore compare how these historic bridges can still be used today. A combination of loads considered were snow, rain, and wind forces. Hand calculations were done by method of joints. The placement for the loading of the weight varied from being uniformly distributed weights on the top chords, that for example is snow, and a single point load of the center bottom bracing or decking used in the bridge, which would represent a compact car. These hand calculations allowed us to see which joints of the bridge were going to have to be more reliable. We decided to also perform a structural analysis using Inventor Professional 2017, in which we modeled the original bridge, selected the exact material, and placed different loads to see how the bridge would react. This in turn gave us a clear understanding of deflections and allowed us to determine which members we would have to pay special attention to. As for example, if you see in the figures, we can conclude that the top chords will point toward each other when the loading is placed in the center. Our solution to that is attaching a horizontal member connecting the top chords, giving it another constraint, and in turn helping us achieve less deflection.
For the historic codes portion of our research, I started searching for publishings made from Vermont and also called the City Hall in Orange County for any information I could get on the Moxie-covered bridge. I was able to find a manual that Vermont uses for the covered bridges. In it, it provides support to those involved with maintaining and rehabilitating covered bridges. This manual took a real deep dive into preserving timber bridges. It goes into depth of how to assess possible problems with the bridge and how to strengthen it so that we can keep them standing for as long as possible. I also found an article published by 2 professors from Iowa State University. They performed an analysis on the bridge that went over its base structure and sizing, as well as a testing that they performed on the bridge. With this analysis, I could determine how the bridge reacts with its current use today. These articles I obtained helped me gain an understanding of why the bridge was built the way it was and what measures they took to preserve it for so long.
Hello, my name is John Ruiz, and I will be presenting the Evaluate Durability section of this project. Now I would like to talk about the durability. Being that this bridge is a covered bridge, we get a few advantages, with the most important being that the outside sheathing protects the wooden structural members and planks from the weather. If we take a look at the picture to the right, some of the things that concerns us is the erosion of the river banks. We see that concrete has already been poured to one side of the bridge and the other is left exposed for the natural elements of erosion to happen. To counter this, placing local boulders or rocks around the base of the bridge allows us to slow the river's current and could help extend this part of the bridge's life. Another thing to consider is taking visual inspections of the bridge, replacing any members as needed. For example, if a metal piece was to appear rusted and in need of replacement, a new piece would be installed and painted a natural color or as close to the bridge's natural color as possible. Lastly, the wooden bridge faces destruction not only from natural elements but from termites and other foul insects. To counter this, using preventative maintenance such as spraying an insecticide to fend off any foul insects would be our best solution, as it would be the most cost-effective and safest way for the bridge to stay alive.
During the student design build portion of this project, we faced a few obstacles. As a part of this competition, we were given certain parameters to stay within, such as height and weight requirements. To meet the weight requirements, we decided to remove certain members that were once included in our original design, and this helped with the efficiency of our bridge, but efficiency wasn't the only challenge we faced. When we scaled the bridge to a 1:10 ratio, the length of the bridge was too short for the requirements, so we increased it to approximately a 1:8 ratio. This helped with the length of the bridge, but made the bridge too tall for the parameters, so that had to be adjusted for as well. During the construction of the bridge, we load tested the mainframe and noticed that the mortise and tenon connection was separating. To compensate for that, we added a metal connection to secure it in place. Overall, through the obstacles we faced, we believe we were able to complete the challenge successfully. Throughout the entire process, we used the following as resources and references.
Hello, we're the Carleton University team for the APT 2020 Conference Student Timber Bridge Design and Build Competition. I'll just introduce our team members now. So Natalie Smith has been our team leader for this year. She's in the second year of her program in her Master's of Applied Science in Civil Engineering at Carleton. Renee Halle, as well as myself, Elise Hamp, are both in our second years of the Masters of Applied Science and Civil Engineering at Carleton as well. And Hoda and Osman and Stephen Smoley are in their final years of their undergrad in Architectural Conservation and Sustainability Engineering at Carleton.
So our bridge design was inspired by the Wakefield Quebec Bridge, which was built in 1915 and rebuilt in 1998 after it had been destroyed by fire. This style of truss was developed in the early 19th century, with its prominent feature being the lattice style truss. So a bit of history about the style of truss. The town plank lattice truss was patented by Ethiel Town in 1820. Its design consists of a web of light planks crossed at an angle of 45 to 60 degrees, with cord members at the top and bottom. Traditionally, the planks are connected at each intersection using wooden pegs called treadles, and the absence of bolts makes for a town's design to be unique as it allows for more rigid connections, reducing the risk of the bridge to warp.
Lattice trusses were popular in the 19th century because they used dimensional lumber as opposed to heavy timber, and they were easy to build. They have a high degree of redundancy because there are so many members. There's a lot of load sharing in the structure. So if one of the lattices breaks, it can transfer load to another member. However, these bridges do tend to have low structural efficiency, meaning that the weight of the bridge is quite large sometimes compared to heavy timber bridges because there is so much raw material. The lattice truss design transfers the load to the supports through the lattices in tension and compression. The members closest to the supports have the highest axial forces, and the bottom cord acts in tension while the top is in compression. These cords were often doubled up to provide extra resistance to the high loads. Large deflections and out-of-plane twisting can sometimes occur under heavy loading.
For the construction of the bridge, the first step was to dimension and cut all the wood required for the construction of the bridge. After the wood was cut, it was placed into position so to confirm that we had all the pieces needed. We then clamped all the pieces into position in order to drill the holes for all the dowel and bolt connections. In teams of 2, we placed the outside cords on the ground for each lattice and inserted the dowels into them. Starting from the outside of the lattice going to the inside, we inserted each layer of the lattice onto the dowels through the holes previously drilled. The end post was then connected to each end of the lattice and fastened with bolts. Once both sides of the bridge were secured, we connected the floor beams to the bottom cords and tie beams to the top cords. Finally, the decking was nailed onto the floor beams.
As a group, we faced several challenges during the transition from phase 2 to phase 3. COVID delayed our material procurement, which resulted in rushed construction. The alignment of lattice members and end posts for drilling due to an initial lack of supporting structure. We had challenges in the alignment of lattice members and end posts for drilling due to an initial lack of supporting structure. We had to overcome a learning curve in the construction, in our construction skills due to our current skill set. We had a challenge in the cross-beam connections as they were designed last minute, which also presented itself during when weighed in. We also had a challenge with technology. We had several limitations in camera, video recording, battery lifespan, and setup. In conclusion, we worked our way around project management basics. We learned to delegate, plan, and prepare. We also learned the application of timber design. Lattice design was included in a lot of our redundant members. Therefore, the importance of design of connections and human error or feasibility of the design was a significant factor in the construction process. What we would do differently is redesign the crossbeam connections to direct forces directly onto the truss cords. We would also improve support structures used during the pre-construction and construction phases by the use of clamps. What was important is that we developed an understanding of historic construction practices through hands-on experience. We use 90% wood materials by weight. Therefore, we do not rely on steel or modern materials to provide strength or elasticity. It was definitely valuable for getting hands-on construction and design practice as students who primarily gain theoretical practice through university courses.
Overall, this whole project would not have been possible without the following individuals. We'd like to thank our faculty advisor and industry members, as well as the Carleton University Faculty of Engineering and Design for supporting us. Also, everyone who helped us in the Carleton lab, including getting access to that. And of course, thank you to the APT PETC competition organizers for setting up this whole thing.